done lithium acid acidation and misnomer acidation procedure. Then we move on to the lithium acid acidation steps in detail. Here we have a natural nucleoside. We are going to convert it into a nucleoside based diphenyl containing acid. So first what we do is we preferentially protect the primary OH group using a reagent called tertiary butyl diphenyl silane chloride in pyridine reagent solvent at room temperature under nitrogen for around 18 hours. This OH group will be protected by tertiary butyl diphenyl silane chloride. And in the second step, we need to convert the secondary OH into a easy leaving triplet group. For that, we will treat it with trifluoromethyl sulfonate chloride and DMAP reagent in DCM solvent under 0 degree for 2 hours. Then OH group will be converted into an easy leaving triplet group. Then after that, lithium acid acidation will be done in the DMF solvent at room temperature for 18 hours. And we can see that the triplet group is absent here. It is replaced by an acid group, and that too stereospecifically. There will be an inversion in configuration. Then and finally, the protection is done using TBAF, that is tetrabutyl ammonium fluoride in THF at room temperature for 2 hours. And finally, we get the siloacidone product, and that too. This product is prepared from adenosine and thymidine nucleoside. Similarly, misnomer oxidation was also done. In the first step, we will protect it using TPDPSCl as we have done before. In the second step, we will do the acidation under misnomer condition, that is in the presence of diad and PPSCl. And DPPA, that is diphenyl phosphoryl acid, is the acidating agent here. And in THF it is done, and the temperature range from 0 to room temperature condition under nitrogen for 7 hours. Then we can see that the OH group present here is directly converted into an acid group, and that too in an inverted configuration. Again, hello sir. The deprotection is done using tetrabutyl ammonium fluoride, and finally we will get the product, and that too is done using thymidine and adenosine molecules. Then about the synthesis of thymidine based puromycin analog via storage and Wilrasa coupling is done. These are the reagents used: HOVT, DIC, TME3, FMOP tyrosine, and THF. And the 0 to room temperature conditions are used under nitrogen for around 6 hours. Moving on to my result and discussion part, we have done a comparison of acidation strategies. That is, we have synthesized the siloacidothymidine and siloacidodeoxyadenosine using misnomer reaction as well as the Schrödinger and lithium acid reaction. And we understood that in misnomer reaction the yield is quite high, that is 82 and 75% yield we got, and for lithium acid it is around 50 and 44. So we can say that the DPPA is an effective in acidation than highly reactive lithium acid. Then acidation is a two-step process in lithium acid strategy, whereas in misnomer it is a single-step process. Also, lithium acid we have to keep all the class pairs under cold condition in order to avoid side reaction. That is a very difficult task. And in misnomer reaction, the only problem we faced was with the formation of PPS3O, which on doing careful column chromatography we can remove PPS3O reagent. Then again a comparative study of N6-amidine protected and unprotected acidation pathways are also done. Here, when we took the adenosine reagent, the amine group has been protected before doing the misnomer acidation. But there is a work in which this amine group is protected first, and then the misnomer acidation is done. Here, we can see that in unprotected pathway we got an yield of 75%, but in the protected pathway, after doing acidation and after doing reprotection, the overall yield again turned out to be 75%. So we suggest this is a greener alternative, that is no need to do any protection before this logo acidation, because the protected pathway, which is a 3-step process, and a single-step unprotected pathway give the same yield. And also this protecting agent DBFDA is synthesized from a hazardous chemical, and it is our unprotected pathway turns out to be a greener one. And about the conformation of stereochemistry of Xylor product, here we have about the conformation of the stereochemistry of the Xylor product. This is a query that was asked from one of our reviewers when we published a paper in Letters in Organic Chemistry. They asked, how did you confirm the stereochemistry only by NMR? And we had cleared the doubt using the paper published by Yamamoto et al. That they have synthesized similar compounds, that is xylo compound and a ribo compound. And in the xylo compound, they found that the CH-CE1 hydrogen appears to be a doublet of doublet, and in the ribo form, the C1 hydrogen appear to be a triplet. So in our case, we got a doublet of doublet, confirming that it is in the xylo form. Then again about the Schrodinger-Wildwasser coupling, we had done the Schrodinger-Wildwasser coupling using HOVT, DIC, PME3 and ethanol tyrosine NTH solvent, and it turns out to be around 20%. So let me summarize my chapter 1. Acido derivatives of nucleoside analogs, xylohexidotymidine and xyloazidodeoxygenose were synthesized using lithium acid and Misnobo reaction. Misnobo reaction was preferred over lithium acid acidation in terms of yield and reaction condition. And also on the comparative study, we found that even our unprotected pathway is more effective, more easier and a greener alternative than the protected one. And also we have coupled the xyloazidothymidine with ethanol protected tyrosine using Schrodinger-Wildwasser coupling reaction. About the future perspectives, we compare the synthetic approaches of puramycin, the traditional method, and Schrodinger-Wildwasser coupling method. We want to do that. Then these are some of the NMR spectrums and Kumsi spectrums we have taken. And moving on to my chapter 2. It's about the study of mechanism using density functional theory. There are two mechanisms are there in my wet lab studies, that is Misnobo acidation and Schrodinger-Wildwasser coupling. In Misnobo acidation, we have identified two pathways and studied using PME3 and DBS3 reagents, and the Schrodinger-Wildwasser coupling pathways were also studied. So about density functional theory, we know that it is one of the most powerful computational tools in theoretical organic chemistry calculation for studying the thermodynamics, molecular geometries, charges, dipole moments, electric potentials, spectroscopic characters, reaction pathways, and in order to conform the mechanistic pathways as well. So about the mechanism study using BFT, we found a paper from which we understood that the Misnobo esterification reaction they have studied, and they have done identified the stereospecific nature and possible side products. Then, but no DFT studies were found for Misnobo acidation, which was found to be a research gap in that area. And the mechanistic pathway of this Schrodinger reaction was also extensively studied by Tian et al., but no DFT studies were there on SP coupling. So for DFT studies, we use the software Gaussian Nayak, and for visualization, we use GaussView 16, and the since correlation functional used is B3lib. and the basis site is 61 plus TDP, and CPCM model, here the solvent used is THF, which we used in our wet lab studies. So we have done Misnobo acidation in our lab, and we need to identify what are the mechanism in this particular reaction, and for that we have a scheme in which we understood that the first step is the formation of a betaine intermediate, and it has two sides, like an electrophilic site and a nucleophilic site, and this give rise to two different mechanistic pathways. And in the pathway A, we named it as pathway A, and here we are adding DPPA to the betaine reagent, and the pathway B means the thymidine is added to the betaine intermediate. Similarly, Schrodinger-Wilrasser coupling, we know that it is a conversion of an acide to an amide group, and here we have identified an intermediate, an important intermediate called iminophosphine, and after that only the coupling reaction will take place. So in order to get an idea, an overall idea, we need to study about the Schrodinger reaction, that is the reaction from the acide to the formation of iminophosphine intermediate, and after that we need to do the DFT calculation for Wilrasser coupling. So about Schrodinger reaction, the PME3 and is the reagent used, and THF is the solvent in the system. And there are three possible attacks are there on the acide by PME3. We call cis attack, trans attack, and gamma attack identified. From that we made a scheme, and it is used for our DFT studies. So Wilrasser coupling also, from iminophosphine, the tyrosine group is linked, and this is the pathway, two steps are identified, and VTS1 and VTS2 are the TS identified for this reaction. So about the resultant discussion, the Misnobo acidation pathway A is studied using two reagents, PME3 and VTS3. These are the scheme that we have used, and there are 4 steps in it. And on analyzing the energy profile, we understood that in the first step there is a formation of betaine, which is a very stable intermediate, and after that DPPA is added to the intermediate, and we got another intermediate. Here the difference activation energy barrier turns out to be around 24. And in the third step, when thymidine is added, the activation energy barrier is very high, that is around 75, and in the final step, it is the activation energy barrier is around 30. So from here, we understood that this particular step, that is the third step, is having a very high activation energy barrier, which says like it is not the reaction mechanism is not possible under room temperature condition with that much of activation, across that much of activation energy. Either we need to provide some energy or use some catalyst, but actually this reaction is happening inside. We have done it in the lab, so we can say that this is not the actual mechanism that's happening inside the system. Similarly, we tried it with PPS3 reagent as well. We got a similar pattern of energy profile. Again, on comparing these two patterns, we found that these patterns are similar, and in the third step, the activation and energy barrier is very high. So this